basic objective of operations in Naval Petroleum Reserve No. 4 has been to explore for oil. All other projects have been secondary. The PET 4 Operating Committee determines the methods to be used, as well as the extent and locations of the exploration. Early in the exploration, the committee had a possible pipeline route surveyed, for any oil found would be useless without an efficient way of getting it out of the reserve. Wide areas in PET 4 have been covered by various geological and geophysical methods. Several wells have been drilled. The objective is oil in commercial quantities. The first step is to find structures favorable to the accumulation of oil. If we were to remove a part of the Earth's surface, we might find an elongated under-earth structure called a closed anticline. If we look at this in cross-section, we see that the strata of rock are upfolded or arched and dip away from the crest in all directions. Such a structure is favorable to the accumulation of oil. In addition, there must be a porous and permeable layer which is overlaid by an impervious layer of caprock. It is this porous and permeable layer that may contain oil. Only one way exists to find out. That is to drill into the structure. In this film, we shall consider the methods of exploring for oil used in PET 4. The basic geological method of exploring for oil is to study the outcrops which are found frequently along rivers and streams in PET 4. A single outcrop gives information on the character of any rock layer, its thickness, the angle between the layer and a horizontal plane, the direction of the dip, and the porosity and permeability of the rock, as we see here, greatly magnified. Several outcrops may permit the geologist to determine this same information for several layers of rock, until with many layers, he has what is called the stratigraphic column of the area, a picture of the entire sequence. A study of additional outcrops gives a picture of closed anticlines in the area. Let us now see how geologists working in PET 4 have used the methods of studying outcrops to determine the character of the rocks and to locate closed anticlines. Sometimes the outcrops are so apparent that visual inspection from an airplane gives a good indication of an area to study in detail. As no dependable maps for the area were available, the Air Force, Navy, and U.S. Geological Survey have cooperated in developing maps by aerial photography for use in exploration studies. Aerial photography is also an excellent basis for selecting areas for outcrop study. The Operating Committee considers the recommendations of the U.S. Geological Survey as to the areas to be studied, the number of parties needed, and the food and gasoline caches necessary to do the job. Food, gas, and oil are cached for each geological party. Bush planes carry the geological parties to their initial stations. At the field station, they set up their balloon silk sleeping tents and the cook's tent. A typical party has 4 men, 2 geologists, a field assistant, and a cook. They break out their collapsible canvas boats and get them in shape for use. Sectional wooden boats have proved less satisfactory. When the work is started, the surveyor sets up his plane table and alidade to shoot in the location of all stations. All outcrops around the initial station are visited. The attitude of the strata are noted. The weathered surface of a rock is studied as well as a freshly broken surface. Samples of rock as well as macrofossil evidence, such as clam shells, are collected for later analysis in the laboratory. The surveyor may be called upon to measure the thickness of the rock layers. In a bed of coal, an uncontaminated sample is taken for laboratory study. Camp is moved when trips to and from outcrops take too much time. Moving for a river party is usually a matter of floating down the river. In places, the rivers contain many large boulders and many rapids. Portaging may be necessary. Or the boats may be lined through by having one man wade alongside the boat in water of 35 to 40 degrees Fahrenheit, while another man helps with a line on the shore. Sometimes the boats must be dragged over bars where the river is wide and shallow. At the new station, the same studying of outcrops and taking of samples continues. Only now, an attempt must be made to correlate the new findings with previous ones. The study of outcrops continues throughout the summer, and supplies from the outside are brought in by plane. Food is backpacked from cache to camp, and daily communication is maintained by portable radio to Umiat, perhaps 250 miles away. Weasel parties are very similar to the river parties, except for the mode of transportation. They leave Umiat after the snow is off the ground. A weasel party has the same staff as a river party, except for the addition of a weasel mechanic. Camp is made, and the geologist goes into the field, measures the dip and strike, and maps the geology of the area. At the end of the field season, parties are returned to base camp by weasel, or float down the river to Umiat. Some are brought back by plane. In the laboratory, the rock samples are carefully studied for porosity, permeability, and the micro and macro fossils, all matters of importance in oil exploration. Back in Washington, the geologists fill in geologic maps, prepare cross-sections, work out stratigraphic columns, and write their reports. With the data on underground structures now assembled, the aerial photographs are restudied, and attempts are made to fill in the structures in interstream areas where there were few outcrops. Outcrop studies have covered considerable areas in PET 4. Core drilling is another method used by geologists to find out what lies beneath the surface of the earth. Sometimes there are no outcrops or too few outcrops to indicate the character of the rock beneath the overburden. In such instances, core drilling gives additional geological information. The procedure in core drilling is generally similar to deep well rotary drilling. A square or octagonal pipe called a kelly is suspended from a swivel. The kelly extends through a rotary drive bushing. Attached to the lower end of the kelly are joints of drill pipe. To the bottom joint of pipe is attached a core barrel and bit. A nearby mud pit furnishes drilling fluid. A hose attached to a pump connects mud pit and kelly. The drilling fluid is pumped through the hose into the kelly and down through the drill pipe. At the bottom of the hole, it picks up the drill cuttings and carries them up into the mud pit, where the cuttings settle to the bottom of the pit. The core hole may be drilled from 300 to 1,400 feet deep, depending on the rig and the information required. Inside the barrel is the core sample, as we see in this cross-section. The hole may be cored at intervals or cored continuously. Also, ditch samples may be taken when required from the discharge line entering the mud pit. The samples from a single hole indicate the stratigraphic column at that locality or the depth drilled. Such core and ditch samples may be used to assist in locating favorable structure as well as stratigraphy. In PET 4, core drilling has been used primarily to determine the stratigraphic column. Let us now see how the actual process of core drilling takes place in PET 4. The job starts in Barrow Base Camp with the usual construction and thorough preparation that must mark all operations in northern Alaska. From January to March, the core drilling equipment is moved out from the base camp. Personnel will go out later by air. On location, camp is set up. The party will eat and sleep and work in these wanigans. The drill rig wanigan and the adjacent mud pit wanigan are the center of core drilling work. This equipment is so constructed that no rigging up is required in the field. The derrick is already up. The portable mud pits are ready. In preparing to drill, the men merely have to put the sleds in position and make a few electrical and flow pipe connections. Inside the rig house is the drilling equipment. Here is the Kelly, which acts as a drive shaft, the swivel which holds the Kelly, and the hose which carries mud into the drill pipe. Here, too, is the drive bushing which rotates the Kelly, the drill pipe, and the bit. In the adjacent mud pit wanigan is the portable mud pit. It contains a mixture of water and pulverized clay particles. Sometimes additives are introduced to change the weight or viscosity of the mud. It is tested 2 or 3 times a day for density, viscosity, and temperature. It is kept warm so that it does not freeze while passing through the permafrost. When the predetermined drilling depth has been reached, the pipe is removed joint by joint. Attached to the last joint is the core barrel and bit. The bit is removed. Then, piece by piece, the core samples are removed, washed, inspected, and placed in a core tray ready for shipment to the laboratory in Fairbanks. In Fairbanks, the samples are carefully analyzed. The information secured is carefully correlated with information secured from other core tests and from study of outcrops. Back in 1944, the Navy Seabees began core holing on the reserve. It continues today, usually during the summer, but may be carried on the year round. To date, 18 core holes have been drilled in Pet 4. One geophysical approach to finding underground structures favorable to oil is magnetometer surveying. The theory is relatively simple. Basement rock underlying sedimentary rock has limited magnetic properties. Thus, variations in the magnetic intensity as measured above the surface may give a tentative picture of the features of the basement. From this, inferences may be drawn as to the probable geologic conditions warranting further exploration by other methods. In Pet 4, aerial magnetometer surveying has been completed over wide areas. A PBY 5A carries the magnetometer aloft. The results of these magnetometer surveys indicate specific areas for further geological and geophysical exploration. Another geophysical approach to underground structures is gravity meter surveying. The theory of gravity meter surveying can be outlined quickly. The closer the basement is to a fixed altitude, the greater the gravitational attraction of the basement. If the amount of gravitational attraction is measured, a tentative picture of the underground mass structure can be made. From this, inferences can be drawn as to the probable geologic conditions and the nature of any underground structures. Gravity meter work in Pet 4 takes place from March to September. The meter is carried from station to station by air. During winter, the plane lands on a frozen river or other likely spot near the survey station. The meter tripod is placed and leveled. The gravity meter is then placed on the tripod. The location is marked by a flag for future reference. The meter has an electrical connection to the plane. This permits the meter to be kept at a constant temperature, a necessity if readings are to be accurate. An altimeter reading is taken so that the gravity meter readings can later be corrected for altitude variations. The gravity meter is then carefully adjusted and read, and all data entered in the field data book. The gear is returned to the plane, which takes off for the next station, usually about 5 miles away. Back at base camp, the data from several stations are plotted on base maps after appropriate corrections. The base map is then used in PET 4 to select areas for investigation by other methods, especially the seismograph. A third type of geophysical exploration occurs in PET 4. It is seismograph surveying by the reflection method. Let us look at the theory involved. A charge exploded beneath the surface sets up seismic waves, which are transmitted by particles of matter. These waves increase in speed when they strike a stratum of increased density. At such points, an energy wave is reflected to the surface and recorded on tape. A part of the wave continues to a lower stratum, where again reflections to the surface occur. If these reflected waves are carefully recorded, timed, and interpreted, a picture of the attitude and depth of the reflecting beds is secured. From several such records of carefully located explosions, one has data from which the subsurface structure may be interpreted. After camp has been set up and equipment serviced, a hole is drilled with the same equipment used for core drilling. These holes are usually from 50 to 100 feet deep. While the shot hole is being drilled, the recording weasel is moved to its position. Connected to this weasel is the cable, which is reeled out along a line already marked by the surveyors. At marked points along the line, holes are dug. The geophones are placed against the ground. Several geophones, 120 feet apart, are connected to the cable. These geophones will pick up the reflected seismic waves and change the wave into an electrical signal, which travels along the cable to the recording weasel. Back at the completed shot hole, dynamite is lowered and the hole tamped by filling with water. As the hole is shot, nearby in the recording weasel, a record is made. The electrical signals from the geophones are stepped up in the amplifier, transmitted to galvanometers, and recorded by the camera. When the shooting is completed, the geophones are detached and the cable reeled in. Several such holes may be shot in one day. At the end of each day, the records are carefully studied by the seismologist. He picks the reflections and marks the time of each reflection in seconds after the shot. He also inserts exact times on the time lines. These data are then used to compute the depth and dip of the reflecting beds. From such information, cross sections are prepared. With sufficient data from many shot holes, structure contour maps of the reflecting strata are made up. This geophysical method is widely used in PET 4, particularly in the Arctic plain, where there are few outcrops. Seismograph surveying continues until about the middle of September. The various geological and geophysical methods so far considered in this film give indications of underground structures favorable to the bearing of oil. To find out if there is oil in the structure, a well must be drilled. 3 deep test wells have been drilled in PET 4. In addition, shallow oil tests have been drilled in connection with core testing. Test well drilling in PET 4 is not very different from drilling elsewhere, except for special problems due to terrain, construction, and the extreme cold. At the well site, supplies and equipment are unloaded. With the start of construction, problems peculiar to PET 4 begin to occur. For winter drilling, the derrick must be completely enclosed with insulating canvas to protect the men and the gear from wind and cold. Even the crown block is enclosed. The rig house connected to the enclosed derrick houses the mud pit and pumps. Inside the rig house, the drilling fluid is heated by steam coils in the mud pit, so that the mud flows readily from the hole deep in the permanently frozen ground. Space heaters in the rig house help keep the drilling fluid warm during cold weather. Heat escaping through the opening to the enclosed derrick keeps the temperature adequate for the workman. The mechanics of drilling in the Arctic are the same as those used anywhere else in the world. A bit is screwed into the drill collar. The drill pipe is screwed together in 80-foot stands and run into the hole. The driller controls the weight on the bit by means of a weight indicator. When the bit becomes dull, the drill pipe is pulled, racked up in 80-foot stands, and the bit removed. The petroleum engineer tests the mud for weight, viscosity, and temperature. When cores are taken, the geologist assembles them in trays, inspects and describes them, and examines them under a microscope. Throughout the drilling, the driller keeps an eye on the gas indicator for possible signs of gas in the drilling fluid. The driller is always ready to operate the remote controls which close the blowout preventer and thus keep mud and tools from being blown from the hole by high-pressure gas and oil. Every 1,000 feet, it is customary in PET 4 for the petroleum engineer to run an electric log as a check on the rock strata penetrated, their content, and their porosity and permeability. The tape record is made by hand recording equipment. Because of the relative lack of knowledge of the PET 4 area, the electric log has not supplanted coring. When the hole has reached its maximum depth, the petroleum engineer makes a temperature survey of the hole. This helps him to determine the thickness of the permafrost. A thermometer is lowered into the hole. Drilling continues the year round, regardless of Arctic conditions of climate and terrain. Present plans call for continuing the exploration for oil in PET 4 through 1953. The work to be done includes 4 seasons of surface geological exploration, 2 seasons of core drilling, 1 season of airborne gravity meter surveying, 4 seasons of seismograph surveying, and 4 years of test drilling, 1 deep test, 1 medium test, and 1 shallow test well each year. The exact location of these wells will be determined from geological and geophysical findings. In addition, the necessary supporting operations are planned. Thus, the Navy continues its search for oil in the Arctic. In this age of oil-powered machines, so important in peace and war, PET 4 holds great promise for making a significant contribution to our national defense and economy.